Hey, I'm Kirsch. Today we're going to be covering the flyback converter and why it fails EMI and how you can do layout properly so it doesn't fail EMI. The biggest issue with flyback converters, power switching converters, is they fail EMI because of large hot loops, and I'll explain what hot loop is later in this video, and also broken return paths. In the next few minutes, I'll show you exactly what you can do to minimize those hot loops and have a solid return path so you don't spend time adding extra components or extra filter circuits to your board for it to work. These are the most effective ways to reduce noise without needing extra components. So before we start, we want to make sure we launch the Allegro X license. Here I have the Allegro X Platinum license and Allegro X Venture for the PCB layout. So don't use the OrCAD license, use Allegro. First, we'll identify the two hot loops in our circuit that control your EMI. Second, I'll show you how we fix the return paths with some layout tips and moves so that you can borrow for your own design. Third, we'll lock in the placement and routing patterns that you should use for any power switching converter, especially the flyback converter, so you can minimize your emissions by design. Now, how does this work? The reason's because of the physics. Electromagnetic emissions are proportional to the amount of loop area, meaning the conductive material on your PCB, times the di dt, that is the change in current with respect to time. So it's how often that current is switching, oscillating, and changing as time progresses, how quickly and often it does over some area of conductive material, in this case, copper. There's no way to get around the fact that your current is changing and switching, so we need to reduce the size of the copper as much as possible to reduce EMI. Now, when you reduce the loop area and you give a return path for that current underneath the forward path where that current is changing and switching very quickly, that's when you really maximize minimize the EMI in that part of the circuit. Okay, so first we'll identify the two hot loops. If I zoom in on my schematic, the hot loop is this VIN. So that top line, VIN, all the way at the top there, going into the primary side of the transformer. This is our transformer T1. Then the bottom side of that transformer, which goes straight to the drain of our switching MOSFET, that is the other part of the hot loop 1. And then finally, the return path is ground for CIN in particular. That's hot loop 1. Hot loop 2 is the secondary side of the transformer, going straight into the wire that goes through that Schottky diode or that diode rectifier, whatever you want to call it. Then the V out trace, and that goes straight to the load that will pull whatever energy is needed. And finally, the return path for the output capacitors. That's hot loop number 2. Within the hot loops, you have these things called the switch node. So you have the switch node here, which goes just after your transformer or just before. And like say you have a buck or buck boost converter, the wire that goes straight into that inductor, that's your switch node and has the most action, the most EMI. Everywhere else on the schematic is pretty slow in terms of your switching frequency or whatever. And these two hot loops are where your emissions are coming from. The good news is that 80% of the fix to these problems is placing the components correctly. To do that, you need to place carefully for physics in the design. Don't worry, I'll walk you step by step through the physics of it so you can visualize what's going on. So looking at the schematic and PCB layout, watch how I cluster the parts. I bring them real close to each other to minimize the loop area. Here I've got my CIN capacitor placed here. This is my transformer. So the capacitor isn't all the way to the left. It is right next to that transformer. Then my MOSFET, that's right next to the transformer as well. Why? Because these traces, like this trace right here, this VIN, placing these components all together lets me route that VIN with copper, big copper pour over the VIN pins, all in a tight area. Notice my drain net. Okay, so I have my copper pour around my drain net right here, right next to that transformer. Let me give you a 3D view so you see the nets more clearly. Here is my drain net. So my drain net is right here on my switching FET. My V in is right here on my transformer, and my C in capacitor is there as well. This minimizes hot loop area number 1. Hot loop area number 2 is this secondary side of the transformer where I have copper pour going straight into my switching diode, and the diode is kissing the output pin on that transformer. Then V out is all of this copper right here, along with stitching vias to some more V out copper on the bottom of the PCB. Lowers that impedance or the inductance. And see here are my 2 C out output capacitors, and then ground for the return path of that hot loop area number 2. Between the primary side of the transformer and the secondary side, I can establish a creepage constraint. That can be done using a keep out area or zone, or your constraint manager to enforce that rule. You'll do it based on your safety standard, whether it's 2.54 millimeters, 6 millimeters, whatever your standard says. So a quick note, current doesn't necessarily take the shortest line. It goes where there's least amount of inductance. Technically speaking, it goes where there's the least amount of impedance. So that takes account inductance and capacitance, but I'll focus on inductance for now. The lowest path of inductance is usually the copper underneath your route, directly underneath where you're routing your trace. So let's say you have your current going on a top trace, it's the lowest inductance is going to be somewhere underneath where that current and field is looking for to return. If you provide a continuous return plane underneath wherever that current is going, so your current trace is on the top and a continuous return underneath that layer, and then you stitch that return near the edges of your traces, your PCB, the field coming off those traces is going to collapse very quickly, and all that ringing that you'll get in your circuit tends to die off. So let's visualize that. Right, so we've got the PCB, and let's take a look at some of these nets. We have the hot loop coming right off the secondary side of that transformer. Underneath here, I need a return path. So see, my return path is everywhere on the PCB where I can put it, essentially. So I've got return all underneath on the second layer, so, or ground if you want to call it, really it's the return path. On the second and third layers underneath that hot loop area over here, underneath my V out. Let me show you my V out. So if I look at V out plus, it's on layer 1 and layer 4. The top and bottom layers of this PCB. The internal layers are both ground. I have return paths for my V out because that's part of hot loop 2 as well. Okay. Then of course for V in, we have our trace. Now this could be a lot closer. I could minimize this by moving this connector straight on top of that transformer. And that's ideally what I should have done, but it's just to show you, you don't want to do this, have this unnecessarily long. That's not good. Okay, but underneath there, I make sure drop as much ground or return path underneath on layers 2 and 3, especially layer 2, underneath that hot loop. The current and the fields coming off of the switching current will immediately go to the lowest impedance path, and usually that's the lowest inductance. With the return path right underneath there, it's gonna boom, find that quickly. And with the stitching vias to ground as well, that's gonna drop the inductance and impedance even more, which is going to attract that field and make that EMI vanish. Speaking of impedance, now is that the full story? If we're talking about impedance, we have to consider capacitance as well. The higher your capacitance is between two copper layers or two copper planes, whatever, two conductive materials, then the lower your impedance is going to be. So it's the inverse to inductance. Why does that matter? Because I'm going to show you the drain of this MOSFET. Now it's nuanced, but here for my drain net, underneath, I don't do any stitching vias from my drain to ground, well, first of all, it's going to short it, so that's not good. Also, notice how I have this gap in the ground underneath my drain net. That's to reduce the parasitic capacitive coupling between the drain and ground. What I could do is with my ground like this, I can add stitching vias around the ground that's around there. So I minimize parasitic capacitive coupling from the drain to ground, but I also still provide a nearby lower impedance zone for the electromagnetic emissions to catch on to the ground copper that has this low inductance. So it's a bit nuanced, but it's a doubly effective method when you're playing with inductances and capacitances to lower that impedance. Because the lower impedance, again, is what the field is looking for, not necessarily the shortest distance in space. All right, so just a quick recap. We highlighted the two hot loops. I showed you how I placed the components to shrink those hot loops. I made sure to route and pour the copper close to the hot loop so that they are minimized in size, but lowered in inductance as well. I also showed you how you can make easy, continuous return path on the copper layer underneath those top layers. That's how you get a quiet power supply without doing a bunch of extra stuff, adding filters and all this unnecessary extra. There are other things you can do with your PCB, like routing the feedback network correctly. For more details on that and the physics, download our design guide where we explain these concepts in more depth. Follow me for more so you can learn how to design with Allegro.